every astronomy textbook told you the Milky Way stretches 100,000 light-years across. That number appeared on classroom posters and scientific papers for 70 years. Scientists now know it captured only part of the picture. The visible stellar disk does span that distance, but the true galaxy extends far beyond where stars stop shining. Invisible matter, stellar rivers, and gas halos push the boundaries to nearly 2 million light-years when you count everything gravitationally bound to our cosmic home. We were not wrong about what we measured. We were wrong about what we failed to measure. The Milky Way is not a neat spiral. It is a gravitational titan whose full extent remained hidden until technology revealed the invisible. If you want to understand how scientists discovered the galaxy's true dimensions and what this means for everything from alien life to cosmic collisions, hit that like button and subscribe. It truly helps more than you know. But for now, make yourself comfortable. Let's begin. The pale river of light stretching across dark skies has captivated human imagination since our ancestors first looked upward and wondered. Ancient Greeks named it Galaxias Kyklos, the Milky Circle. Aboriginal Australians saw it as a river carrying the spirits of the dead. Norse mythology described it as the path to Valhalla. Polynesian navigators used its position to guide their canoes across thousands of miles of open ocean. None of them understood what they were actually seeing. For most of human history, the Milky Way represented an impenetrable mystery. Was it a celestial river flowing through the heavens? A crack in the dome of the sky letting divine light shine through? The accumulated glow of countless departed souls? Ancient philosophers debated these possibilities without any means of testing their speculations. The technology required to transform speculation into knowledge would not exist for nearly 2,000 years after the first recorded attempts to explain the phenomenon. Aristotle proposed that the Milky Way was a meteorological phenomenon, an ignition of hot gases in the upper atmosphere caused by the motion of stars. This explanation satisfied Greek intellectual traditions for centuries despite being completely wrong. Democritus came closer to the truth, suggesting the glow might result from distant unresolved stars, but his hypothesis could not be verified and was largely ignored by subsequent thinkers. When Galileo Galilei pointed his primitive telescope toward the Milky Way in 1610, he made a discovery that shattered millennia of speculation. That continuous glow resolved into countless individual stars, packed so densely that unaided human eyes blurred them together into a luminous stream. The heavens contained far more suns than anyone had imagined, and they clustered together in patterns that demanded explanation. Galileo's telescope was remarkably crude by modern standards. Its lenses produced blurry images plagued by chromatic aberration. Its magnification power barely exceeded what a modest pair of modern binoculars provides. Yet this simple instrument revealed a universe vastly more populous than any philosopher had dared imagine. Where the naked eye saw smooth luminescence, the telescope revealed stellar multitudes beyond counting. But how many stars? How far did they extend? What shape did this stellar congregation take? These questions would occupy astronomers for centuries, and the answers they eventually reached would prove spectacularly incomplete. The decades following Galileo's discoveries saw telescopes improve dramatically. Larger lenses gathered more light, revealing fainter stars. Better optical designs reduced distortions that plagued early instruments. Astronomers began systematic surveys of the night sky, cataloguing thousands of stellar positions with increasing precision. Yet the fundamental question of galactic structure remained unanswered. Stars seemed scattered everywhere, but did they form a coherent system? Did the distribution have boundaries? Was our sun located at any particular position within the stellar swarm? William Herschel attempted the first systematic survey of the Milky Way in the 1780s. His method was straightforward in concept but grueling in execution. He pointed his telescope in hundreds of different directions, counted the stars visible in each field of view, and used these counts to estimate how stellar density varied across the sky. Where stars appeared most numerous, he reasoned, the galaxy must extend farthest. Herschel was not merely an observer, but also a talented telescope builder. He constructed instruments far superior to anything commercially available, grinding his own mirrors from speculum metal and achieving magnifications that revealed details invisible to lesser equipment. His dedication bordered on obsession. He spent entire nights at the eyepiece, sometimes observing continuously for hours, while his sister Caroline recorded his observations and kept him supplied with food and drink. The star counts he accumulated numbered in the thousands. Each field of view required careful examination, counting every visible point of light while estimating the relative brightness of each star. The work demanded extraordinary patience and meticulous record-keeping. Errors in any single count would propagate through subsequent analysis, potentially distorting conclusions about galactic structure. Herschel concluded that our Sun sat near the center of a lens-shaped stellar system, roughly 5 times longer than it was wide. He imagined the galaxy as a flattened disk with the solar system occupying a privileged central position. This picture aligned comfortably with human assumptions about cosmic importance. If Earth circled a special star, naturally that star would reside at the heart of the stellar realm. He was wrong about nearly everything. The Sun does not occupy the galactic center. The galaxy is not simply lens-shaped, and his size estimates fell short by factors of thousands. But Herschel established a principle that would guide all subsequent mapping efforts. You can deduce the structure of something by carefully counting what it contains and noting where those contents concentrate. The fatal flaw in Herschel's method was something he could not have known existed. Interstellar space is not transparent. Vast clouds of microscopic dust particles float between the stars, absorbing and scattering visible light from distant stellar populations. These dust clouds create dark patches that early astronomers interpreted as genuine gaps in the stellar distribution rather than cosmic fog blocking their view. The composition of interstellar dust remained unknown until the 20th century. We now understand these particles consist primarily of silicates and carbon compounds, microscopic grains smaller than the wavelength of visible light. They form in the outer atmospheres of dying stars and in the expanding remnants of supernova explosions. Over billions of years, this stellar exhaust accumulated throughout the galactic plane, creating a haze that dims and reddens light from distant sources. Imagine trying to map a forest while standing inside it during a thick fog. Trees near you remain visible, but distant groves disappear into grey obscurity. You might conclude the forest ends where visibility fails, never suspecting that millions more trees stand hidden beyond your perception. This was precisely the situation facing early galactic cartographers. Herschel noticed dark regions in the Milky Way and interpreted them as genuine holes in the stellar distribution, tunnels of emptiness through which we could peer into the blackness beyond the galaxy. He called these dark patches openings in the heavens. In reality, they were dense dust clouds blocking our view of the countless stars behind them. The famous coal sack near the Southern Cross, the Great Rift splitting the summer Milky Way, and numerous smaller dark nebulae throughout the galactic band all represent foreground obscuration rather than true voids. This systematic error caused Herschel and subsequent astronomers to dramatically underestimate galactic dimensions. Stars hidden behind dust clouds could not be counted, making distant regions appear empty when they actually teemed with stellar populations. The visible galaxy seemed smaller and more compact than it truly was, because so much of it remained invisible behind cosmic smoke screens. The confusion persisted for over a century. Astronomers debated whether spiral nebulae, mysterious pinwheel-shaped glows visible in large telescopes, were nearby gas clouds within our stellar system, or distant galaxies comparable to the Milky Way. The question could not be resolved without reliable distance measurements, and those remained frustratingly imprecise for objects beyond the nearest stellar neighborhoods. The breakthrough that revealed our true position came from Harlow Shapley in 1918. Shapley studied globular clusters ancient spherical swarms containing hundreds of thousands of stars gravitationally bound together. These clusters orbit the galactic center on elliptical paths that carry them high above and below the dusty galactic plane, where most obscuring material concentrates. Globular clusters represent some of the most ancient objects in the galaxy. They formed over 12 billion years ago, when the Milky Way was still assembling from primordial gas clouds and smaller protogalactic fragments. The stars within each cluster share common origins, having condensed from the same parent gas cloud in relatively brief episodes of coordinated star formation. The chemical composition of globular cluster stars reflects conditions in the early universe. They contain far fewer heavy elements than younger stellar populations, because those heavy elements had not yet been manufactured. Stars create elements heavier than hydrogen and helium through nuclear fusion in their cores, then distribute these products through supernova explosions and stellar winds. Early in galactic history, few stars had lived and died, so raw materials for star formation remained chemically primitive. Because globular clusters rise above the cosmic fog, they remain visible across vast distances. Shapley used a class of pulsating stars called Cepheid variables to measure distances to dozens of these clusters. Cepheid stars brighten and dim in regular cycles, with the period of variation directly related to their intrinsic luminosity. Measure the pulsation period, calculate the true brightness, compare to apparent brightness, and geometry reveals the distance. Henrietta Swan Leavitt had discovered this period luminosity relationship in 1912 while studying Cepheid variables in the Magellanic Clouds. She noticed that brighter Cepheids pulsated more slowly, following a precise mathematical relationship. This discovery transformed Cepheids into cosmic yardsticks. For the first time, astronomers possessed a reliable method for measuring distances to objects far beyond the reach of parallax techniques. Parallax, the apparent shift in position of nearby objects when viewed from different angles, works well for measuring distances to stars within a few hundred light-years. Earth's orbit around the Sun provides a baseline roughly 186 million miles across. Stars observed from opposite sides of Earth's orbit appear to shift slightly against the background of more distant objects. The amount of shift reveals the distance through simple trigonometry, but parallax angles become vanishingly small for more distant stars. Even the most precise instruments of Shapley's era could not detect parallax shifts for objects more than a few hundred light-years away. Cepheid variables provided a way around this limitation. Their pulsation periods could be measured regardless of distance, and those periods revealed intrinsic brightness, which combined with apparent brightness yielded distance. When Shapley plotted the three-dimensional positions of globular clusters, a striking pattern emerged. They did not distribute evenly around the Sun, as would be expected if we occupied the galactic center. Instead, they concentrated heavily toward the constellation Sagittarius, revealing that the true center lay roughly 26,000 light-years away in that direction. The distribution formed an enormous halo surrounding a point nowhere near our solar system. Globular clusters orbited that distant center like bees swarming around a hive, their spatial arrangement revealing the gravitational heart of the galaxy. We occupied an unremarkable position in the outer regions, far from the central concentration of mass that governed galactic dynamics. This discovery displaced humanity from cosmic centrality for the second time in scientific history. Copernicus had shown that Earth was not the center of the solar system. Now, Shapley demonstrated that the solar system was not the center of the galaxy. We inhabited the suburbs, not downtown. Our apparent importance shrank with each new measurement. The psychological impact of this displacement should not be underestimated. For millennia, humans had assumed their position in the cosmos held special significance. Earth occupied the center of creation, or at least the center of our stellar neighborhood. Shapley's work demolished this assumption with ruthless mathematical precision. We were peripheral, occupying no privileged position within the vast stellar system we called home. Shapley's work also provided the first reliable estimate of galactic scale. His measurements suggested the Milky Way stretched approximately 100,000 light-years from edge to edge. This figure, refined slightly over subsequent decades, would become the standard answer, appearing in textbooks, documentaries, and classroom lectures for generations. The measurement technique was elegant but fraught with potential errors. Cepheid variables in globular clusters could be difficult to identify among the dense stellar backgrounds. Period measurements required observations spanning multiple pulsation cycles. Calibrating the period-luminosity relationship demanded knowing the true distances to at least some Cepheids through independent methods. Each step introduced uncertainties that accumulated through the calculation chain. Later, astronomers would refine Shapley's estimates, correcting for various systematic errors he could not have anticipated. The distance to the galactic center would be revised downward to approximately 26,000 light-years, and the overall galactic diameter would be adjusted based on improved understanding of stellar populations and interstellar absorption. But the fundamental picture Shapley established proved correct. The Sun orbited far from the galactic center, and the galaxy itself spanned distances measured in tens of thousands of light-years. 100,000 light-years. The number rolls off the tongue easily enough, but truly grasping what it represents requires sustained effort. Light travels at 186,282 miles per second. Nothing in the universe moves faster. This cosmic speed limit represents the absolute maximum velocity at which information, energy, or matter can traverse space. In the time it takes you to blink, light crosses roughly 18,600 miles, nearly 3/4 of Earth's circumference. A beam of light could circle Earth 7.5 times in a single second. It reaches the Moon in just under 1 1/3 seconds. Light from the Sun requires 8 minutes and 20 seconds to reach Earth, meaning we always see our star as it appeared over 8 minutes in the past. The nearest stars beyond the Sun lie over 4 light-years away, meaning their light began its journey before you started reading this sentence. In 1 year, light covers approximately 5,878,000,000,000 miles. Astronomers call this distance a light-year, and it serves as the standard measuring stick for cosmic scales. The number itself defies intuition. 5 trillion miles means nothing to brains evolved for tracking prey across African savannas. We lack the cognitive architecture to genuinely comprehend such distances. Human spatial intuition evolved to handle distances relevant to survival on the African plains where our ancestors lived. We developed excellent abilities to judge whether a predator was close enough to pose an immediate threat, whether prey was within throwing distance of a spear, whether a water source was close enough to reach before nightfall. These distances ranged from a few feet to perhaps a few dozen miles. Our brains simply did not need to process interstellar distances. Evolution provides capabilities that enhance survival and reproduction, not those required for contemplating cosmic scales. When we try to genuinely comprehend a light year, we are asking mental machinery designed for hunting and gathering to perform tasks utterly outside its design specifications. Now multiply that incomprehensible distance by 100,000. The traditional galactic diameter spans roughly 588 quadrillion miles. Writing out that number in full requires 18 digits. 588,000 trillion miles. Perhaps comparisons to human experience can help bridge the comprehension gap. If you could drive a car at highway speeds across the galaxy, maintaining a steady 65 miles per hour without stopping for fuel, food, or sleep, the journey would require approximately 1,032,000,000,000 years. You would need to maintain that pace for roughly 75 times longer than the current age of the universe. Consider what that means. The universe has existed for approximately 13.8 billion years since the Big Bang initiated cosmic expansion. In all that time, your hypothetical car would have crossed less than 2% of the galactic diameter. Even the fastest objects humans have ever constructed would fail spectacularly at crossing such distances. The Parker Solar Probe, humanity's speediest spacecraft, reaches velocities exceeding 400 to 30,000 miles per hour during its closest approaches to the Sun. At this blistering pace, crossing the traditional galactic diameter would still require roughly 156 billion years. The Voyager probes, launched in 1977, travel at approximately 38,000 miles per hour relative to the Sun. They represent humanity's first objects to enter interstellar space, having passed beyond the heliosphere that marks the Sun's influence. Yet, at their current velocities, the Voyager spacecraft would require over 70,000 years just to reach the nearest neighboring star, a journey covering only a tiny fraction of galactic dimensions. Only light itself can traverse galactic distances within timeframes relevant to cosmic evolution, and even light, the ultimate cosmic speedster, needs 100,000 years for the journey across the traditional Milky Way measurement. Consider what this means for observation. When astronomers study stars on the far side of the galaxy, they see those stars as they existed 100,000 years ago. The light arriving at telescopes tonight began its journey when Neanderthals still walked the Earth. When modern humans had barely begun migrating out of Africa, when written language lay tens of thousands of years in the future. Every photograph of our galaxy captures multiple time periods simultaneously. Light from distant stellar populations reveals ancient history, conditions that prevailed when early humans were developing stone tools. Light from the galactic center departed before the last ice age ended. We never observe the Milky Way as it currently exists, but rather as a composite image blending countless moments across 100 millennia. This temporal displacement affects our understanding of galactic structure. Changes occurring at the galactic center right now will not become visible to Earth-based observers for 26,000 years. Stars that exploded millennia ago may still appear in our telescopes exactly as they did before their destruction, because the light from those explosions has not yet reached us. The traditional picture of galactic structure described a barred spiral galaxy with multiple arms winding outward from a central elongated bar of stars. Two major spiral arms dominate the structure, the Perseus arm and the Scutum Centaurus arm, with additional smaller arms and spurs adding complexity to the overall pattern. These arms contain the galaxy's youngest stellar populations, regions where new stars continue forming from collapsing clouds of hydrogen gas. The spiral pattern does not consist of fixed groups of stars rotating together like spokes on a wheel. Instead, the arms represent density waves, regions where matter temporarily concentrates as it orbits the galactic center. Stars pass through the arms rather than residing permanently within them, like cars moving through a traffic jam. The jam persists even as individual vehicles enter and exit. The spiral arms glow blue-white with the light of massive hot stars that burn through their nuclear fuel in mere millions of years. These stellar giants live fast and die spectacularly, exploding as supernovae that seed surrounding space with heavy elements forged in their cores. Because massive stars have such short lifetimes compared to the time required to orbit the galaxy, they never travel far from their birthplaces before exploding. This is why hot blue stars concentrate in spiral arms where star formation occurs. Between the spiral arms stretch regions dominated by older, cooler stars. These interarm zones contain less gas for star formation, creating apparent gaps in the galactic pinwheel when viewed from outside. Red and yellow stars of lower mass populate these regions. Their more modest energy output, allowing them to shine for billions of years as they slowly orbit through the disk. The overall visual impression resembles a cosmic hurricane, with spiral bands extending outward from a dense central eye. But unlike terrestrial hurricanes that rotate as coherent structures, galactic spiral patterns maintain their shape through more subtle gravitational dynamics. The inner regions orbit faster than outer regions, a phenomenon called differential rotation. If spiral arms were material structures, differential rotation would wind them progressively tighter until they disappeared. Instead, density wave theory explains how the pattern persists despite the differential motion of individual stars. That central region houses the galactic bulge, a dense spheroidal concentration of predominantly old stars surrounding the supermassive black hole at the galaxy's heart. This black hole, designated Sagittarius A star, packs roughly 4 million times the Sun's mass into a region smaller than Mercury's orbit around our own star. The evidence for this central black hole accumulated over decades of careful observation. Astronomers tracked individual stars orbiting near the galactic center, measuring their velocities and orbital paths with extraordinary precision. Some of these stars move at speeds exceeding 10 million miles per hour as they swing past the central object. The orbital motions reveal the mass of whatever they orbit, and that mass is far too concentrated to be anything other than a black hole. Matter falling toward this cosmic drain releases tremendous energy. Though our central black hole currently feeds at a relatively modest rate compared to the voracious active nuclei powering some distant galaxies, quasars, blazars, and active galactic nuclei in other systems shine with luminosities exceeding entire galaxies, powered by supermassive black holes consuming stellar material at prodigious rates. Sagittarius A star, in contrast, swallows only modest amounts of gas and produces correspondingly modest radiation. The visible stellar disk measures roughly 1,000 light-years thick in the outer regions where our solar system orbits, thickening substantially toward the center where the bulge dominates. This thin disk hosts most ongoing star formation, containing enough hydrogen gas to fuel stellar birth for billions of years to come. Our solar system sits within the disk approximately 26,000 light-years from the galactic center, orbiting along with the local stellar neighborhood at roughly 500,000 miles per hour. At this velocity, we complete one orbit approximately every 230 million years, a period sometimes called a galactic year. The Sun has completed roughly 20 orbits since it formed 4.5 billion years ago. Above and below the galactic plane extends a sparse stellar halo, populated by ancient stars and the globular clusters Shapley used to determine our position. These halo objects follow elliptical orbits that carry them far from the crowded disk, plunging through the plane twice per orbit before swinging back into the emptier regions above and below. Many halo stars rank among the oldest in the galaxy, dating back over 12 billion years to when the Milky Way was still assembling from smaller fragments. Their orbits often show no particular alignment with the disk, suggesting they formed before the disk established its current configuration, or were captured from smaller systems that merged with our galaxy early in its history. The traditional measurement focused almost exclusively on the visible disk, because that was what optical telescopes could detect. Astronomers drew the galactic boundary where star counts dropped toward zero, defining the edge as the point where the galaxy simply stopped containing observable objects. This approach seemed perfectly reasonable. How else would you define a galaxy's size except by where its stars end? The answer involves looking at wavelengths of light that human eyes cannot perceive and detecting matter that emits no light at all. 20th century astronomy relied heavily on optical telescopes sensitive to the same wavelengths that human vision detects. Stars emit most of their energy in visible light, so counting stars meant looking with instruments tuned to what eyes could theoretically see. This created systematic blind spots that astronomers did not fully appreciate until new technologies opened alternative windows on the cosmos. The electromagnetic spectrum extends far beyond the narrow slice visible to human eyes. Radio waves have wavelengths measured in centimeters to meters. Infrared radiation lies between radio and visible light. Ultraviolet, X-rays and gamma rays have progressively shorter wavelengths and higher energies than visible light. Each portion of the spectrum reveals different cosmic phenomena, and each requires specialized instruments for detection. Infrared telescopes pierce through dust clouds that block optical wavelengths, revealing stellar populations hidden behind cosmic fog. The same interstellar dust that frustrated Herschel and confused generations of astronomers becomes nearly transparent at infrared wavelengths. Stars that appeared absent in optical surveys shine clearly when observed in infrared light. Radio telescopes detect hydrogen gas, extending far beyond where visible stars become undetectable. Hydrogen atoms emit radiation at a characteristic wavelength of 21 centimeters. When electrons flip their spin orientation relative to protons, this emission is extraordinarily weak from individual atoms, but accumulates to detectable levels across vast interstellar gas clouds. Radio surveys revealed that hydrogen gas extends well beyond the stellar disk, tracing galactic structure where no stars shine. X-ray observatories reveal superheated plasma surrounding the galaxy in enormous halos, invisible to optical instruments. Gas heated to millions of degrees emits strongly at X-ray wavelengths, but produces almost no visible light. Space-based X-ray telescopes, necessary because Earth's atmosphere blocks X-rays from space, uncovered hot, gaseous components completely unknown to earlier astronomers. Each new observational capability exposed galactic components that traditional surveys had completely missed. The Milky Way we thought we knew was like measuring an iceberg by photographing only the portion above water. The visible tip hints at deeper structures lurking beneath the observational surface, but vastly underestimates the total volume. Even within the visible realm, the challenge of measuring from inside the galaxy created insurmountable obstacles for early astronomers. Imagine standing in the middle of a vast forest, attempting to determine where the forest ends. Trees surround you in every direction. Some stand closer, others farther. Fog obscures distant groves. How would you establish the forest's boundaries? You might walk in one direction until trees become sparse, then declare that edge reached. But forests do not terminate abruptly. Trees thin gradually toward meadows and clearings. At what density does forest become non-forest? The boundary depends entirely on your definition and your ability to detect faint, distant specimens. Astronomers faced exactly this dilemma. Stars become increasingly sparse toward the galactic outskirts, but they never completely disappear. Extremely faint dwarf stars scatter through regions that appear empty to moderately sensitive instruments. Red dwarf stars, the most common stellar type in the galaxy, produce so little light that they remain invisible beyond relatively short distances. A census counting only visible stars systematically misses the most numerous stellar population. The boundary between galaxy and intergalactic space blurs rather than sharpens, fading gradually rather than ending crisply. Any line drawn to mark the galactic edge represents an arbitrary decision about what minimum stellar density counts as inside versus outside. Different definitions yield different boundaries, none more correct than others. The 100,000 light-year estimate represented a reasonable consensus, given the observational limitations of mid-20th century astronomy. It captured the visible stellar disk with fair accuracy, but it missed something enormous hiding in plain sight, or rather, hiding in plain darkness. That something would not reveal itself until astronomers noticed that stars at the galactic edge moved in ways that violated the laws of physics as they understood them. The visible galaxy could not possibly account for what the measurements showed. Either Newton's equations were wrong after centuries of successful application, or something massive and invisible was pulling the strings of galactic dynamics. The mystery of the missing mass would ultimately reveal that the galaxy we thought we knew represented merely the luminous core of a far vaster structure, extending into realms of darkness that traditional astronomy could not penetrate. Every calculation built on the 100,000 light-year figure would eventually require revision. The textbook diagrams were not exactly wrong about what they depicted, but they were catastrophically incomplete about what they failed to include. The visible stars form just one component of a galactic system, whose true dimensions would shock even the astronomers who first glimpsed the hidden architecture. The Milky Way was not a disk of stars floating in cosmic emptiness. It was something far stranger, far larger, and far more invisible than anyone had suspected. And the first hints of this hidden reality came from measuring how fast things spin. Stars do not sit motionless in space. Every stellar furnace in the galaxy orbits the galactic center, pulled inward by gravity, while angular momentum prevents them from falling straight in. This cosmic merry-go-round spins perpetually, with stars tracing orbital paths that take millions of years to complete. The physics governing these motions dates back over 3 centuries to Isaac Newton's revolutionary insights. Newton recognized that the same force pulling apples toward Earth also holds the Moon in orbit and keeps planets circling the Sun. Gravity reaches across empty space, pulling every piece of matter toward every other piece with a strength proportional to their masses and inversely proportional to the square of the distance between them. This inverse square law has profound implications for orbital dynamics. Double the distance from a gravitating body and the gravitational pull drops to 1/4. Triple the distance and it falls to 1/9. Objects far from the central mass experience dramatically weaker gravitational attraction than objects nearby. The balance between gravitational pull and orbital motion determines how fast objects must move to maintain stable orbits. An object moving too slowly will spiral inward, unable to resist the gravitational attraction pulling it toward the center. An object moving too fast will escape entirely, flying off into space on an unbound trajectory. Only at precisely the right velocity can an object maintain a stable orbit, continuously falling toward the central mass while simultaneously moving sideways fast enough to keep missing it. The Sun participates in this galactic rotation, carrying Earth and the entire solar system along at roughly 500,000 miles per hour relative to the galactic center. At this velocity, we complete one orbit approximately every 230 million years. Dinosaurs dominated Earth the last time our solar system occupied its current galactic position. The Great Permian extinction that wiped out 90% of marine species occurred roughly 2 orbits ago. One complete circuit of the galaxy spans geological epochs. During each galactic orbit, the solar system passes through spiral arms where dense gas clouds concentrate. Some scientists have proposed that these passages might correlate with mass extinction events on Earth. As the solar system encounters more debris and experiences enhanced cosmic ray bombardment within the arms, the evidence for such correlations remains controversial, but the basic premise that our cosmic environment changes throughout each galactic orbit is well established. Understanding how fast objects orbit reveals how much mass pulls them inward. This relationship follows directly from Newton's laws of gravitation, which have successfully described celestial motions for over 3 centuries. More mass means stronger gravitational attraction, means faster orbital velocities required to balance inward pull against outward momentum. The mathematics works out elegantly. For a circular orbit, the orbital velocity depends only on the mass enclosed within that orbit and the radius of the orbit itself. Measure how fast something orbits and at what distance, and you can calculate the mass responsible for that motion. This technique has been used to weigh everything from binary star systems to the supermassive black hole at the galactic center. In our solar system, this relationship creates a predictable pattern. Mercury, closest to the Sun, orbits fastest at roughly 107,000 miles per hour. Venus moves more slowly at 78,000 miles per hour. Earth moves more slowly still at 67,000 miles per hour. Mars, Jupiter, Saturn, Uranus, and Neptune orbit at progressively slower velocities as their distances from the Sun increase. Distant Neptune crawls along at just 12,000 miles per hour. Orbital speed decreases with distance from the central mass because gravitational pull weakens with increasing separation. This pattern, called Keplerian rotation after Johannes Kepler, who first described planetary orbital laws, applies wherever mass concentrates at a central point. The outer regions of a system experience weaker gravity and therefore require slower orbital velocities to maintain equilibrium. Any deviation from this pattern would indicate that the assumed mass distribution was incorrect. Astronomers expected the Milky Way to follow the same pattern. Most visible mass concentrates toward the galactic center in the bulge and inner disk regions. Roughly half of all stellar light comes from the inner quarter of the galactic disk. The rotation curve, plotting orbital velocity against distance from the galactic center, should decline steadily as you move outward. The expectation seemed so obviously correct that early measurements were designed primarily to confirm it. The Sun's orbital velocity, combined with the distance to the galactic center, yielded an estimate of enclosed mass. Extending such measurements to other distances would simply refine the details of how mass distributed throughout the visible disk. Measuring stellar velocities across the galaxy requires detecting Doppler shifts in starlight. When a star moves toward us, its light waves compress slightly, shifting the spectrum toward bluer wavelengths. When a star moves away, light waves stretch toward redder wavelengths. The amount of spectral shift reveals the velocity, allowing astronomers to track motion across distances where direct observation of movement would require millions of years. The Doppler effect applies to all wave phenomena. You experience it when an ambulance siren sounds higher-pitched while approaching and lower-pitched while receding. Light waves behave similarly, though detecting the shifts requires precise spectroscopic measurements. Characteristic absorption lines in stellar spectra provide reference points whose wavelengths are known from laboratory measurements. Comparing observed wavelengths to laboratory values reveals whether the star moves toward or away from the observer and at what speed. Early rotation curve measurements focused on regions within a few thousand light-years of the Sun. These nearby measurements showed orbital velocities broadly consistent with expectations, though uncertainties were large. Extending measurements to the outer galaxy required observing hydrogen gas clouds rather than individual stars, since gas extends farther than easily observable stellar populations. Hydrogen atoms emit radio waves at a characteristic wavelength of 21 centimeters. This emission occurs when the electron in a hydrogen atom spontaneously flips its spin orientation relative to the proton. The transition is extraordinarily unlikely for any individual atom, occurring on average once every 10 million years. But the galaxy contains so many hydrogen atoms that the cumulative emission becomes detectable by radio telescopes. The 21-centimeter observations revealed hydrogen gas extending well beyond the visible stellar disk. More importantly, Doppler shifts in this radio emission revealed gas velocities at distances far from the galactic center. These measurements provided the first hints that something was seriously wrong with conventional assumptions about galactic mass distribution. When Vera Rubin and Kent Ford compiled rotation velocity measurements for the Milky Way and numerous other spiral galaxies during the 1970s, they found something that should have been impossible. The rotation curve stayed flat. Stars and gas clouds at the galactic edge orbited at essentially the same velocities as material much closer to the center. The expected Keplerian decline never materialized. Outer regions moved far too quickly for the visible mass to explain their orbital paths. Rubin faced considerable skepticism when she first presented these results. The astronomical community was slow to accept conclusions that violated long-held assumptions about galactic structure. Some suggested her measurements contained systematic errors. Others proposed that the mass distribution in spiral galaxies might differ from standard models in ways that could explain flat rotation curves without invoking invisible matter. But Rubin's work was meticulous. She and Ford observed multiple galaxies using spectrographic techniques that provided velocity measurements across entire galactic disks. Each galaxy showed the same pattern. Rotation velocities rose quickly in the inner regions, as expected, then flattened to nearly constant values extending far beyond where most visible matter resided. The phenomenon was not a peculiarity of one or two unusual systems, but a universal characteristic of spiral galaxies. According to Newtonian physics, those outer stars should have been flung into intergalactic space long ago. The visible galaxy cannot possibly hold them in orbit. The gravitational pull from all observable matter falls pathetically short of what would be required to maintain the measured velocities. Consider the mathematics. If the galaxy contained only the visible mass, concentrated in the inner regions, orbital velocity should decline proportionally to the square root of the enclosed mass divided by radius. Beyond the visible disk, where little additional mass would be encountered, velocities should drop off roughly as the inverse square root of distance. At twice the radius, velocity should be about 70% of what it was closer in. At 3 times the radius, it should drop to about 60%. Instead, velocities remained constant or even increased slightly with distance. At the outermost measurable points, orbital speeds exceeded predictions based on visible mass by factors of 2 or more. The discrepancy was not subtle. It represented a fundamental mismatch between observations and theory, yet there the outer stars remain, happily orbiting at speeds that violate every prediction based on luminous matter alone. Either Newton's equations fail at galactic scales, a possibility that centuries of successful application made unlikely, or something invisible was providing the missing gravitational attraction. Testing whether Newtonian gravity fails at large scales became an active research program. Modified Newtonian dynamics, proposed by physicist Mordechai Milgrom in 1983, suggested that gravitational attraction might strengthen at very low accelerations typical of galactic outskirts. This modification could explain flat rotation curves without requiring invisible matter. The modified gravity hypothesis made testable predictions that differed from dark matter models. Observations of galaxy clusters, gravitational lensing effects, and the cosmic microwave background radiation consistently favored dark matter over modified gravity. While some researchers continue exploring modified gravity alternatives, mainstream astrophysics has largely concluded that invisible matter provides the most coherent explanation for the observed phenomena. Swiss astronomer Fritz Zwicky had anticipated this problem decades earlier. In the 1930s, Zwicky studied the Coma Galaxy Cluster, a rich collection of over 1,000 galaxies bound together by mutual gravitational attraction, roughly 320 million light-years from Earth. He measured how fast individual galaxies moved relative to each other within the cluster using Doppler shifts in their spectra. Zwicky applied a technique called the virial theorem, which relates the average kinetic energy of objects in a gravitationally bound system to the total gravitational potential energy holding them together. The theorem allows calculating total mass from observed velocities, regardless of how that mass is distributed or whether it emits detectable radiation. His calculations yielded shocking results. The galaxies moved far too fast. Their velocities exceeded what the visible galaxies could gravitationally support by a factor of roughly 400. The cluster should have flown apart billions of years ago, its member galaxies scattering into the cosmic void like an explosion frozen in time. Zwicky proposed that some form of invisible matter must pervade the cluster, providing gravitational glue that observations could not detect. He called this hypothetical substance Dunkelmaterie in German, translated to English as dark matter. The name reveals almost nothing about its actual nature. Zwicky could not have known what dark matter was made of, only that it must exist to explain the gravitational dynamics he observed. The astronomical community largely ignored Zwicky's conclusions for decades. His abrasive personality and tendency toward grandiose claims made colleagues reluctant to take his work seriously. The dark matter hypothesis seemed too radical, requiring the existence of vast quantities of undetected material pervading the universe. Surely, some conventional explanation would eventually emerge. Rubin's rotation curve measurements 4 decades later vindicated Zwicky's insight. Dark matter was not merely a curiosity of galaxy clusters, but a fundamental component of individual galaxies themselves. Every spiral galaxy she studied showed the same flat rotation curves. The phenomenon was universal, demanding a universal explanation. The evidence continued mounting from independent directions. Gravitational lensing observations, measurements of the cosmic microwave background radiation, studies of how galaxies cluster on large scales, and computer simulations of cosmic structure formation all pointed toward the same conclusion. Dark matter exists in enormous quantities, outweighing visible matter by roughly 5-to-1 throughout the universe. The cosmic microwave background provides particularly compelling evidence. This radiation, released roughly 380,000 years after the Big Bang when the universe cooled enough for atoms to form, carries subtle temperature fluctuations, reflecting density variations in the early cosmos. The pattern of these fluctuations depends sensitively on the relative amounts of ordinary matter, dark matter, and dark energy in the universe. Precise measurements by satellites, including COBE, WMAP, and Planck, constrain these ratios with remarkable precision, consistently indicating that dark matter comprises roughly 27% of the universe's total energy content, while ordinary matter accounts for only about 5%. Galaxy cluster collisions provide direct visual evidence for dark matter's existence. The Bullet cluster, observed in 2006, consists of two galaxy clusters that collided and passed through each other roughly 150 million years ago. During the collision, the hot gas comprising most of the ordinary matter in clusters interacted electromagnetically, slowing down and separating from the galaxies themselves. Dark matter, interacting only gravitationally, passed through without slowing. Gravitational lensing reveals where mass actually resides in the Bullet cluster, while X-ray observations show where the hot gas ended up. The mass concentrations do not coincide with the gas. Instead, they trace the locations of the visible galaxies, demonstrating that most cluster mass consists of something other than the hot gas that dominates ordinary matter content. Dark matter provides the only coherent explanation for this separation. Over subsequent decades, increasingly sophisticated measurements refined our understanding of dark matter's distribution. It does not concentrate at galactic centers like visible stars. Instead, dark matter forms vast spherical halos that extend far beyond the luminous disk, wrapping visible galaxies in invisible gravitational scaffolding. The density profile of dark matter halos follows a characteristic pattern identified through computer simulations and confirmed by observations. Density rises toward the center, reaching a peak somewhere near the galactic core, then declines steadily with increasing radius. The mathematical form describing this distribution, called the Navarro-Frenk-White profile, after the researchers who first characterized it, has become a standard tool for modeling galactic dark matter. Unlike the flattened disk formed by visible matter, dark matter halos are roughly spherical. This shape difference arises from the different physics governing each component. Ordinary matter can radiate energy through electromagnetic processes, allowing it to cool and collapse into thin rotating disks. Dark matter cannot emit radiation and therefore cannot dissipate energy efficiently. It settles into more extended, roughly spherical configurations determined by gravitational dynamics alone. Current estimates indicate that dark matter outweighs visible matter in the universe by a ratio of approximately 5:1. For every star, planet, asteroid, gas cloud, and dust grain that telescopes can detect, this invisible majority dominates cosmic structure while remaining completely undetectable except through gravitational influence. Despite decades of effort, no one knows what dark matter actually is. The leading hypothesis suggests it consists of some type of elementary particle not included in the standard model of particle physics. These hypothetical particles would need to interact very weakly with ordinary matter, explaining why they have evaded detection despite presumably pervading our cosmic neighborhood. Weakly interacting massive particles, whimsically abbreviated as WIMPs, represent one popular candidate. These hypothetical particles would have masses roughly 100 times that of a proton and would interact through the weak nuclear force in addition to gravity. Such particles would have been produced abundantly in the hot early universe, with just the right density surviving to the present day to explain observed dark matter abundance. Experiments around the world attempt to detect WIMPs directly. Deep underground laboratories shield sensitive detectors from cosmic rays and other background radiation that would overwhelm any dark matter signal. The detectors wait for rare interactions between passing dark matter particles and ordinary atomic nuclei, which would deposit tiny amounts of energy detectable by extremely sensitive instruments. Despite increasingly sophisticated searches spanning several decades, no convincing WIMP detection has occurred. This null result has progressively eliminated parameter space where WIMPs might hide, though the hypothesis remains viable for certain mass ranges and interaction strengths. Each generation of experiments probes weaker interactions and smaller masses, gradually cornering the remaining possibilities. Axions represent another dark matter candidate. Originally proposed to solve problems in quantum chromodynamics, unrelated to cosmology, these hypothetical particles would be extraordinarily light, perhaps 1 trillion times less massive than electrons, but could have been produced in sufficient quantities during the early universe to account for observed dark matter abundance. Axion detection experiments exploit the particle's predicted ability to convert into photons within strong magnetic fields. More exotic possibilities include primordial black holes formed from density fluctuations in the early universe, self-interacting dark matter that would clump differently than standard cold dark matter, and even modifications to gravity that might mimic dark matter effects. None of these alternatives has gained widespread acceptance, but the failure to detect conventional particle dark matter has renewed interest in exploring unconventional options. The particle nature of dark matter matters enormously for understanding galactic structure. Different types of dark matter would produce different density profiles, different small-scale structures, and different predictions for how galaxies form and evolve. Current observations favor cold dark matter, meaning particles that moved slowly compared to light speed when structures began forming. Hot dark matter, composed of fast-moving particles like neutrinos, would have smoothed out small-scale density fluctuations, preventing the formation of structures we actually observe. In the Milky Way, the dark matter halo extends vastly farther than the visible stellar disk. While stars become sparse beyond 50 or 60,000 light-years from the galactic center, the dark matter envelope continues outward for hundreds of thousands of light-years, eventually fading into the general cosmic background. The Sun sits within this dark matter halo, surrounded by invisible particles streaming through our cosmic neighborhood. Calculations suggest roughly 1 dark matter particle passes through every cubic centimeter of space each second, totaling perhaps 100,000 particles passing through your body every second. You never notice because dark matter interacts so weakly that it passes through ordinary matter like light through glass. This local dark matter density, roughly equivalent to 1 proton mass per 3 cubic centimeters of space, provides targets for direct detection experiments. The denser the local dark matter, the more frequently particles should interact with detector material. Understanding dark matter distribution within the galaxy helps experimenters interpret their results and plan future searches. Mapping this invisible structure requires ingenious techniques, since you cannot photograph something that produces no electromagnetic radiation whatsoever. Astronomers exploit gravitational lensing, the bending of light paths by massive objects as predicted by Einstein's general relativity. Einstein recognized that mass curves the fabric of space-time itself. Light traveling through curved space-time follows curved paths, even though photons have no mass and do not experience gravitational attraction in the Newtonian sense. The effect was first confirmed during the solar eclipse of 1919, when stars near the Sun's position appeared slightly displaced from their normal positions due to the Sun's gravitational bending of their light. Galaxies and galaxy clusters produce much stronger lensing than individual stars. When light from a distant galaxy passes near a foreground concentration of mass, gravity curves the light's path substantially, distorting the distant galaxy's apparent shape. Circular sources become stretched into arcs. Multiple images of the same background object can appear at different positions around the foreground lens. In extreme cases, background sources are smeared into complete rings surrounding the lensing mass. The amount of distortion reveals how much mass the light encountered, regardless of whether that mass shines or hides in darkness. Mass bends space-time. Space-time bending bends light. The amount of bending reveals the mass. By measuring how background galaxy images warp around foreground objects, astronomers can reconstruct mass distributions that include both visible and invisible components. Gravitational lensing studies consistently reveal that galaxies contain far more mass than their luminous portions suggest. Dark matter halos typically extend at least 10 times farther than visible stellar populations. The optical galaxy is merely the bright ornament atop an enormous invisible pedestal. Weak gravitational lensing, which produces subtle distortions undetectable in individual background galaxies but measurable statistically across many galaxies, allows mapping dark matter distributions throughout the universe. These maps reveal the cosmic web, the vast network of dark matter filaments connecting galaxy clusters across billions of light years. Galaxies form within this web, concentrated at nodes where filaments intersect. For our Milky Way specifically, constraining the dark matter halo's dimensions proves challenging because we observe from inside the structure we are trying to measure. We cannot step outside to photograph the halo's extent or measure how background objects lens around our galaxy. Instead, astronomers must infer halo properties from indirect evidence. The total mass of the Milky Way, including both visible and dark components, falls somewhere between 1 and 4 trillion times the Sun's mass. Different measurement methods yield somewhat different values, with uncertainties remaining substantial. The range reflects genuine difficulty in measuring the outer halo, rather than sloppy science. Visible components account for only a fraction of this total. Stars contribute roughly 50 to 100 billion solar masses. Interstellar gas adds perhaps another 10 to 20 billion solar masses. Dust contributes negligibly to the mass budget despite its visibility in blocking background light. Together, these components account for at most a few percent of the galaxy's gravitational mass. Even accepting the lower mass estimates, dark matter dominates by an overwhelming margin. Perhaps 80 to 90% of the Milky Way's mass resides in the invisible halo. The stars we admire on clear nights represent the minority population, the visible tip of an enormous dark iceberg. This mass distribution fundamentally alters how we conceptualize galactic structure. The traditional picture imagined a disk of stars floating in essentially empty space, its gravity confined to the regions where light shines. The corrected picture reveals that disk is embedded within a massive dark sphere that dwarfs the visible component in both mass and spatial extent. Think of an egg. The yolk at the center represents the visible galaxy with its stars, gas clouds, and central black hole. The egg white surrounding the yolk represents the dark matter halo, vastly larger in volume though less immediately obvious. You cannot understand the egg by examining only the yolk. Computer simulations of dark matter halo formation suggest that these structures emerged naturally from the physics of the early universe. Shortly after the Big Bang, tiny quantum fluctuations in matter density created regions slightly more or less dense than average. These fluctuations, imprinted during the inflationary epoch that preceded the hot Big Bang, were extraordinarily small, varying from mean density by only about 1 part in 100,000. Gravity amplified these tiny variations over billions of years. Overdense regions attracted more matter, growing progressively larger while underdense regions emptied into their surroundings. The process proceeded hierarchically, with small structures forming first and merging into progressively larger ones over cosmic time. Dark matter, whatever it actually is, does not interact with light, and therefore could begin clumping together before normal matter, while ordinary atoms remained trapped in a hot plasma soup during the universe's first few 100,000 years. Unable to collapse gravitationally because radiation pressure supported them against gravity, dark matter was already condensing into gravitational structures. Freed from electromagnetic interactions, dark matter particles responded only to gravity, falling into overdense regions and amplifying the density contrasts. By the time ordinary matter could finally collapse, roughly 380,000 years after the Big Bang, when electrons and protons combined into neutral atoms, dark matter had already created a scaffolding of gravitational potential wells. Ordinary matter fell into these pre-existing structures, collecting at the centers of dark matter halos where gravity was strongest. Gas accumulated in these halos, compressed under its own weight, and eventually fragmented into the first stars. These stars collected into the first galaxies, surrounded by the dark matter halos that had gathered them. The visible galaxies we observe today retain this fundamental architecture. Luminous cores surrounded by dark matter envelopes that formed earlier and extend farther. The Milky Way's dark matter halo thus predates its visible stars. The invisible component formed first, creating a gravitational well that subsequently captured the gas that collapsed into stellar populations. We live inside a structure whose foundation was laid before the first star ignited anywhere in the universe. This chronology has been confirmed through observations of the cosmic microwave background, measurements of primordial element abundances, and detailed comparisons between simulated and observed cosmic structures. The sequence of dark matter collapse followed by ordinary matter accumulation, followed by star formation, represents our best understanding of how galaxies came to exist. Determining where the dark matter halo ends poses conceptual as well as observational challenges. Dark matter density decreases gradually, with distance from the galactic center, following the Navarro-Frank-White profile, or similar mathematical forms. The density never reaches zero but asymptotically approaches the average dark matter density of the universe at large distances. Where exactly does the halo end and intergalactic space begin? The question has no unique answer because the transition is gradual rather than sharp. Different definitions of the boundary yield different sizes, none more physically correct than others. The galaxy fades into its surroundings rather than ending at a definite edge. What remains unambiguous is that the galaxy extends vastly farther than mid-20th century astronomers imagined. The dark matter halo adds an enormous invisible territory surrounding the visible stellar disk. When someone asks how big the Milky Way is, the honest answer depends entirely on what components you include. The discovery of dark matter dominance raised immediate questions about galactic dynamics. A galaxy several times more massive than visible matter alone would suggest exerts proportionally stronger gravitational influence. It can capture and retain objects that lighter estimates suggested should escape. The Milky Way is not the medium-sized spiral described in older textbooks. Accounting for dark matter reveals a galactic heavyweight, one of the more massive structures in the local universe. Our cosmic address became far more significant than earlier measurements suggested. But dark matter represents just one component of the extended galactic structure. Additional observations would reveal further structures spreading into the cosmic darkness, confirming that the visible galaxy represents merely the innermost region of a far vaster gravitational entity whose true boundaries remain to be defined. Measuring dark matter through its gravitational effects on starlight and galaxy rotations reveal that the Milky Way extends far beyond its visible disk, but gravitational lensing and rotation curves provide only indirect evidence about where the galaxy truly ends. To trace the outer boundary directly, astronomers needed visible objects orbiting at extreme distances, test particles revealing the gravitational field through their motions. Nature provides exactly such traces in the form of ancient stellar rivers wrapping around the galactic halo like luminous threads on an invisible sphere. Stellar streams represent forensic evidence of cosmic violence preserved across billions of years. The Milky Way does not exist in isolation. Dozens of smaller galaxies orbit within its gravitational sphere, remnants of the hierarchical assembly process that built all large galaxies. When these smaller systems venture too close to the galactic center, tidal forces seize them with devastating consequences. Tidal disruption occurs because gravity varies with distance. The side of a small galaxy facing the Milky Way experiences stronger gravitational pull than the far side. This difference in force stretches the victim, pulling stars away from their original positions. Over millions of years, the unfortunate dwarf galaxy elongates into a ribbon of stars tracing its orbital path through space. The physics mirrors what happens to comets approaching the Sun or moons orbiting too close to giant planets. The Roche limit defines the distance within which tidal forces exceed the self-gravity holding an object together, Cross inside this boundary and you get torn apart. The precise distance depends on the density of both objects, but the outcome is always the same: destruction through gravitational stretching. For dwarf galaxies approaching the Milky Way, the Roche limit extends to enormous distances. A loosely bound dwarf galaxy, containing perhaps 1 billion stars spread across several thousand light-years, faces tidal disruption beginning hundreds of thousands of light-years from the galactic center. The disruption proceeds gradually, stripping outer stars first while the dense core survives longer. But eventually the entire system unravels into a stellar stream. These streams do not disperse randomly into space. Each star within a stream follows an orbit determined by the Milky Way's gravitational field, tracing paths that reveal the underlying mass distribution. Stars stripped from the leading edge of a disrupting galaxy move slightly faster than the parent system and pull ahead along the orbit. Stars stripped from the trailing edge move slightly slower and fall behind. The result is an elongated stream stretched along the orbital trajectory, marking the path like breadcrumbs through the dark forest of the outer halo. The Sagittarius stream provides the most spectacular and thoroughly studied example of this phenomenon. Its parent system, the Sagittarius dwarf elliptical galaxy, currently ranks as the closest known galaxy to the Milky Way's center at a distance of roughly 70,000 light-years. This proximity proves fatal. Tidal forces have been shredding Sagittarius for at least 2 billion years, stretching its stars into an enormous stream wrapping completely around our galaxy. The discovery of the Sagittarius dwarf itself came surprisingly late in astronomical history. Despite its proximity, the galaxy hides behind the dense star fields of the galactic bulge as viewed from Earth. It was not identified until 1994, when astronomers noticed a concentration of stars with unusual velocities and chemical compositions in the direction of Sagittarius. Follow-up observations revealed a dwarf galaxy in the final stages of tidal destruction. Mapping the associated stream required observing stars distributed across the entire sky. The stream wraps around the Milky Way at least twice, with stars scattered along a path extending over 1 million light-years in total length if you trace the entire orbital arc. Different portions of the stream lie at different distances from us, some relatively nearby at 50,000 light-years, others far beyond the visible disk, at distances exceeding 200,000 light-years. The stream's geometry provides powerful constraints on the Milky Way's mass distribution. Stars in the stream follow ballistic trajectories through the galactic gravitational field, responding to the total mass enclosed within their orbits, regardless of whether that mass shines or hides in darkness. Computer models simulate stream formation under different assumptions about galactic mass and shape, then compare predicted stream paths to observed stellar positions. The models that best match observations reveal the true mass distribution. These analyses consistently indicate that substantial mass extends far beyond the visible stellar disk. The Sagittarius stream could not maintain its observed configuration if the galaxy contained only the mass visible in stars and gas. Gravitational attraction from an extended dark matter halo is required to explain the stream's detailed structure. The Gaia spacecraft revolutionized stream studies by measuring precise positions and velocities for over 1 billion stars. Launched by the European Space Agency in 2013, Gaia operates at a special gravitational balance 1.5 million kilometers from Earth, where it systematically surveys the entire sky. Its instruments measure stellar positions with accuracy exceeding 10 micro-arcseconds for bright stars, roughly equivalent to resolving a human hair from 1,000 kilometers away. Beyond positions, Gaia measures proper motions, the apparent drift of stars across the sky caused by their actual movement through space. These angular velocities, combined with distance estimates from parallax measurements, reveal three-dimensional space velocities for hundreds of millions of stars. The resulting dataset allows astronomers to trace stellar orbits through the galaxy with unprecedented precision. Gaia data revealed stream structures invisible to previous surveys. Stars, sharing common origins in disrupted systems, move through space with similar velocities, clustering not only in position but in velocity space. Algorithms designed to identify such clusters within Gaia's massive database have discovered dozens of previously unknown streams threading through the galactic halo. The GD1 stream, discovered in 2006 but fully characterized using Gaia data, traces a thin ribbon of stars through the northern galactic halo. Unlike the Sagittarius stream, which originated from a dwarf galaxy, GD1 appears to have formed from a disrupted globular cluster. Its narrow width and coherent structure make it particularly valuable for constraining the gravitational field through which it orbits. Intriguingly, GD1 shows gaps and density variations along its length that cannot be explained by the smooth gravitational field of the visible galaxy, plus a standard dark matter halo. These perturbations suggest that something punched through the stream, gravitationally scattering stars from their original positions. The most likely culprit is a dense clump of dark matter, a subhalo containing no stars but enough mass to disrupt the stream upon passage. If confirmed, such features would provide direct evidence for the lumpy substructure that cold dark matter models predict should pervade galactic halos. The orphan stream acquired its name because astronomers could not initially identify its parent system. This stream orbits on a highly inclined path, carrying stars through regions far above and below the galactic plane. For years, no known satellite galaxy or globular cluster matched the stream's trajectory or stellar chemistry. Recent evidence suggests the progenitor may have been a dwarf galaxy that has now been completely dispersed, leaving only the stream as evidence of its former existence. Palomar 5 represents a globular cluster caught in the act of tidal destruction. This ancient star cluster, located roughly 76,000 light-years from Earth, has developed prominent tidal tails, extending thousands of light-years in both directions along its orbit. Computer simulations indicate that Palomar 5 will be completely dispersed within the next billion years, its stars scattered along a stream indistinguishable from the remnants of other destroyed clusters. Each stream discovery adds another tracer, revealing the galaxy's gravitational extent. Streams at moderate distances constrain mass in the inner halo. Streams orbiting far from the galactic center probe the outer regions where dark matter density drops toward background levels. The most distant confirmed stream stars orbit past 300,000 light-years from the galactic center, demonstrating that gravitational binding extends to remarkable distances. Stars at 300,000 light-years require enormous timescales to complete their orbits. Moving at typical halo velocities of perhaps 100 kilometers per second, such stars need roughly 2 billion years per orbit. Since the streams formed from disruption events occurring within the past few billion years, these distant stars have circled the galaxy only once or twice since their parent systems were destroyed. Yet, they remain gravitationally bound, proving that the Milky Way's influence extends at least this far. Satellite galaxies provide complementary information through an entirely different observational approach. Rather than tracing debris from destroyed systems, astronomers can study intact companions still orbiting within the Milky Way's gravitational sphere. The properties of these satellites, particularly their distances and orbital velocities, constrain the total mass holding them captive. The Magellanic Clouds have been observed since prehistoric times, appearing as detached patches of the Milky Way visible from the southern hemisphere. Aboriginal Australians incorporated them into Dreamtime stories. Polynesian navigators used them for celestial orientation. European explorers named them after Ferdinand Magellan, whose 16th century expedition first reported them to European audiences. Modern observations reveal the Large Magellanic Cloud as an irregular galaxy containing roughly 30 billion stars spread across a region approximately 14,000 light-years in diameter. The Small Magellanic Cloud contains perhaps 7 billion stars in a more compact configuration. Both clouds orbit the Milky Way, while also interacting gravitationally with each other, creating complex dynamics that have puzzled astronomers for decades. The distance to the Large Magellanic Cloud, approximately 160,000 light-years, places it well beyond the visible stellar disk but firmly within the dark matter halo. At this distance, The cloud requires roughly 1.5 billion years to complete an orbit around the Milky Way, assuming a roughly circular trajectory. Whether the Magellanic Clouds have completed multiple orbits or are approaching for only the first or second time remains debated, with implications for how the Milky Way captured them. Recent proper motion measurements from Gaia suggest the Magellanic Clouds may be moving faster than previously thought, raising questions about whether they are truly gravitationally bound or merely passing through our neighborhood on unbound trajectories. If the clouds are indeed bound, the Milky Way must be more massive than some estimates suggest to retain them. If they are unbound, they represent intergalactic visitors rather than permanent satellites. Beyond the Magellanic System orbit numerous smaller dwarf galaxies discovered through systematic surveys of the outer halo. These ultra-faint dwarfs contain only thousands to tens of thousands of stars, making them extraordinarily difficult to detect against the foreground of Milky Way stars. They appear not as discrete objects visible to casual observation, but as subtle statistical overdensities revealed only through careful analysis of stellar catalogues. The Sloan Digital Sky Survey, which imaged large portions of the northern sky during the early 2000s, discovered numerous ultra-faint satellites, including Ursa Major I, Ursa Major II, Boötes, and several others. The Dark Energy Survey subsequently discovered additional satellites in the southern sky, including Reticulum II, Horologium I, and Tucana II. Each new deep survey reveals additional candidates at the boundaries of current detection sensitivity. These ultra-faint dwarfs pose significant challenges for theories of galaxy formation. Standard models predict that dark matter halos should contain numerous smaller subhalos, each potentially hosting a dwarf galaxy. The predicted number far exceeds the count of observed satellites, creating the missing satellites problem that has motivated extensive theoretical investigation. Possible solutions include the destruction of small satellites by tidal forces, the failure of star formation in the smallest halos, or genuine problems with cold dark matter predictions on small scales. The most distant confirmed satellite galaxies orbit near 1 million light-years from the galactic center. Leo I, a dwarf spheroidal galaxy, lies approximately 850,000 light-years away, making it one of the most remote Milky Way companions. Determining whether such distant objects are truly bound to our galaxy requires precise velocity measurements combined with accurate mass estimates for the Milky Way itself. Satellite orbits depend directly on the total mass, holding them gravitationally bound. A satellite at a given distance will escape if it moves faster than the escape velocity at that distance, which in turn depends on all the mass within that orbital radius. Measuring satellite velocities thus constrains galactic mass, regardless of how that mass divides between visible and invisible components. This technique has been applied to the Milky Way's satellite population using velocity measurements from spectroscopic surveys. The resulting mass estimates consistently fall in the range of 1 to 4 trillion solar masses, depending on which satellites are included and what assumptions are made about their orbital characteristics. The satellites themselves demonstrate that binding mass extends far beyond the visible disk. A third major component of the outer galaxy remained essentially unknown until technological advances allowed its detection. The circumgalactic medium consists of hot, diffuse gas, pervading the enormous volume between the visible disk and the virial radius boundary. This gaseous envelope was predicted theoretically long before observations confirmed its existence. Galaxies form from gas that falls into dark matter halos, but not all infalling gas reaches the central regions where star formation occurs. Some gas shock heats as it encounters the galaxy's gravitational potential well, raising its temperature to millions of degrees. At such extreme temperatures, the gas becomes too hot to cool efficiently and collapse further. Instead, it remains suspended in an extended halo, supported against gravitational collapse by its own thermal pressure. The physics resembles what happens in galaxy clusters, where hot intracluster gas fills the space between member galaxies and emits X-rays detectable by orbiting observatories. The circumgalactic medium around individual galaxies is less dense and therefore much fainter. But the same basic physics applies. Gas heated to millions of degrees glows at X-ray wavelengths while remaining invisible to optical telescopes. Detecting the circumgalactic medium around the Milky Way proved extraordinarily difficult because we observe from inside the structure. Any telescope on Earth, or in near-Earth orbit, looks through the circumgalactic medium in all directions, creating an all-sky glow rather than a discrete object that can be imaged against a dark background. Separating local circumgalactic emission from other sources of diffuse X-ray background required decades of careful analysis. Absorption spectroscopy provided the first definitive detections. When light from a distant quasar passes through intervening gas, atoms in that gas absorb light at characteristic wavelengths corresponding to electronic transitions. The absorption features appear as dark lines superimposed on the quasar's spectrum. Identifying which absorption systems arise in the circumgalactic medium versus intergalactic space, or gas, associated with other galaxies requires careful analysis of velocities and line strengths. Observations using the Hubble Space Telescope's Cosmic Origins spectrograph have detected highly ionized oxygen, carbon, and silicon in absorption toward numerous background quasars. The ionization states indicate gas temperatures of hundreds of thousands to millions of degrees, consistent with theoretical predictions for circumgalactic material. The velocities match expectations for gas associated with the Milky Way rather than more distant systems. X-ray observations provide complementary evidence. The ROSAT satellite, launched in 1990, detected diffuse soft X-ray emission from all directions in the sky. More recent observations from XMM Newton and Chandra have characterized this emission in greater detail. While separating local bubble emission from circumgalactic emission remains challenging, the observations confirm substantial hot gas surrounding our galaxy. Current estimates suggest the circumgalactic medium contains mass comparable to all the stars in the visible galaxy combined, roughly 50 to 100 billion solar masses of hot gas spread across the enormous volume of the outer halo. This represents a significant reservoir of material available for future star formation, though the gas must cool substantially before it can collapse into molecular clouds and ultimately into stars. The circumgalactic medium participates in a galactic baryon cycle that regulates star formation over cosmic time. Gas flows inward from intergalactic space, shock heats upon encountering the galaxy's potential well, and gradually cools through radiative processes. Eventually, cooled gas reaches the disk and participates in star formation. Stellar winds and supernova explosions return processed material to the halo, where it mixes with freshly accreted gas before potentially cycling back to the disk. This circulation means the circumgalactic medium continuously exchanges material with both the interstellar medium within the disk and the intergalactic medium beyond the halo. The boundary between circumgalactic and intergalactic gas becomes particularly fuzzy, with no sharp transition separating material bound to the galaxy from material participating in cosmic flows between galaxies. The extent of detectable hot gas reaches several 100,000 light-years from the galactic center, before emission and absorption signatures drop below. Beyond this distance, the circumgalactic medium merges gradually into the intergalactic medium, the even more diffuse gas pervading the voids between galaxies throughout the universe. Combining information from stellar streams, satellite galaxies, and the circumgalactic medium creates a picture of the outer Milky Way that would have astonished astronomers working just decades ago. The visible disk, with its spiral arms and central bulge, represents merely the bright inner core. Surrounding that luminous center spreads an enormous domain of sparse stars, disrupted satellites, hot plasma, and overwhelming quantities of invisible dark matter. Drawing the galaxy's boundary requires choosing among several physically meaningful definitions that yield substantially different answers. Each definition captures something real about galactic structure, while emphasizing different aspects of the complex transition between galaxy and intergalactic space. The optical radius, where visible starlight fades below detection thresholds, gives roughly 50 to 60,000 light-years in most directions. This corresponds approximately to the traditional 100,000 light-year diameter that appeared in mid-20th century textbooks. The optical boundary remains useful for characterizing the visible galaxy but misses most of the total structure. The gaseous disk of neutral hydrogen extends somewhat farther than the stellar disk, perhaps 70 to 80,000 light-years before column density drops dramatically. This gas represents raw material for future star formation that has not yet collapsed into stars. Radio observations at the characteristic 21 centimeter wavelength reveal this extended gaseous component, tracing structure beyond where optical surveys find significant stellar populations. The stellar halo, including disrupted satellite debris and ancient native populations, stretches to at least 300,000 light-years based on detected stream stars. These sparse outer stellar populations orbit on elliptical trajectories that carry them far from the disk, sampling the gravitational field at enormous distances. Individual halo stars have been identified beyond 400,000 light-years, though such extreme objects are extraordinarily rare and difficult to confirm. The hot circumgalactic medium extends several 100,000 light-years in observational detections, though theoretical models suggest it likely continues farther at densities below current sensitivity limits. The transition between circumgalactic and intergalactic gas occurs gradually over hundreds of thousands of light-years rather than at any definite boundary. Satellite galaxies orbit within roughly 1 million light-years while remaining gravitationally bound, though the exact boundary between bound satellites and unbound interlopers requires careful dynamical analysis. Objects near this boundary may be marginally bound, destined to escape over cosmic timescales as the universe continues expanding. The virial radius provides the most physically motivated boundary definition. This radius marks the sphere within which matter has reached approximate gravitational equilibrium. Given the universe's finite age, within the virial radius, infalling material has time to orbit at least once before cosmic expansion could carry distant matter beyond gravitational reach. Outside the virial radius, the universe's expansion begins dominating over gravitational attraction. For the Milky Way, current mass estimates place the virial radius at approximately 800,000 to 1 million light-years from the galactic center. This enormous distance exceeds the visible disk diameter by factors of 15 to 20. The sphere enclosed by the virial radius has a diameter approaching 2 million light-years. Beyond the virial radius, matter generally flows outward with cosmic expansion rather than remaining permanently bound to the galactic gravitational well. However, the transition is not sharp. Some material slightly outside the virial radius will eventually fall inward as gravitational attraction gradually overcomes expansion. Other material slightly inside might escape if it possesses sufficient velocity. The boundary represents a statistical concept rather than a physical barrier. The splashback radius offers yet another boundary definition, marking where infalling material reaches maximum distance on first approach before gravity reverses its outward motion. Material crossing the splashback radius for the first time is definitionally entering the galaxy's sphere of influence. This radius typically exceeds the virial radius by 10 to 20%, extending the effective galactic boundary even farther. The turnaround radius goes further still, marking where cosmic expansion and gravitational attraction precisely balance for material that has never previously interacted with the galaxy. Beyond the turnaround radius, material recedes forever with the expanding universe. Inside, material will eventually fall toward the galactic center. Current estimates place the Milky Way's turnaround radius near 2 million light-years, meaning our galaxy's gravitational influence extends to distances approaching the separation to Andromeda. If we accept the virial radius as the operationally meaningful galactic boundary, the Milky Way spans roughly 1.6 to 2 million light-years in diameter. This figure exceeds the traditional 100,000 light-year measurement by a factor of 16 to 20. The galaxy is not slightly larger than textbooks claimed. It is vastly, overwhelmingly, incomprehensibly larger. The problem with defining galactic size is that galaxies do not possess edges in any familiar sense. There is no wall marking where Milky Way territory ends and intergalactic space begins. No customs checkpoint demands identification from incoming particles. No fence separates our gravitational domain from the territory of neighboring systems. Matter thins gradually with distance from the galactic center. Star density drops from millions per cubic light year in the bulge to perhaps 1 per 1,000 cubic light years in the outer halo, to functionally 0 in intergalactic space. Dark matter density follows a similar but gentler decline, dropping by factors of thousands between the galactic center and the virial radius. Gas density varies enormously depending on whether you sample the dense molecular clouds of the disk, the diffuse circumgalactic medium, or the nearly empty intergalactic void. None of these transitions occurs at a definite radius. Density drops asymptotically towards 0 without ever quite reaching it. Stray atoms of galactic origin undoubtedly float through regions millions of light years from the visible disk, escaped from the circumgalactic medium, or flung outward by ancient supernova explosions. At what density does galactic material become intergalactic material? The question has no unique answer. The boundary between galaxy and not galaxy depends entirely on what definition you adopt and what components you choose to count. This ambiguity frustrates tidy categorization, but accurately reflects genuine physical reality. The universe does not organize itself according to human preferences for clean demarcations and precise borders. Perhaps the most useful perspective abandons the notion of the galaxy as a discrete object with definable edges, and instead recognizes the Milky Way as a gravitational basin embedded within cosmic structure. Within a certain radius, everything falls toward the center or orbits around it, caught in the gravitational web woven by accumulated mass over billions of years. Beyond that radius, cosmic expansion dominates and material recedes forever, carried away by the stretching of space itself. The transition between these regimes marks the galaxy's effective limit, even though no physical barrier exists. The virial radius approximately captures this transition, though the boundary remains fuzzy rather than sharp. Material near the boundary may be marginally bound or marginally unbound, depending on its precise velocity and trajectory. By any reasonable definition, including more than just visible starlight, the Milky Way spans at least several 100,000 light-years and plausibly approaches 2 million. The 100,000 light-year figure captures the visible stellar disk while missing the vast dark matter halo. The sparse stellar halo extending far beyond the disk, the hot circumgalactic medium pervading the outer regions, and the satellite galaxies orbiting within the gravitational sphere of influence. We live inside a cosmic entity far larger than humanity imagined throughout most of our species' existence. The faint ribbon of light crossing dark skies, the feature that gave our galaxy its name, represents the bright inner fraction of an enormous dark sphere, extending 15 to 20 times farther into the cosmic void. The Milky Way does not drift alone through cosmic emptiness. Our galaxy belongs to a gravitational community called the Local Group, a collection of over 80 galaxies bound together by mutual attraction, despite the universe's relentless expansion, stretching distant structures apart. This cosmic neighborhood represents the smallest scale at which galaxies organize into coherent gravitational systems, the first rung on a ladder of structure extending to the largest scales observable. The concept of the Local Group emerged in the 1930s when Edwin Hubble recognized that several nearby galaxies shared similar distances and motions through space. Unlike more distant galaxies receding with cosmic expansion, these neighbors moved in ways suggesting gravitational binding. They orbited common centers of mass, approached and receded from each other, and maintained proximity across cosmic timescales when unbound objects would have scattered. The Local Group spans roughly 10 million light-years across its longest dimension. A vast territory by human standards, but modest compared to larger galactic structures. Within this volume, gravitational attraction exceeds the stretching effect of cosmic expansion. Member galaxies remain bound together, orbiting within a shared gravitational well that has persisted since the early universe. Two giants dominate this gravitational community: our Milky Way and the Andromeda Galaxy. These spiral systems contain the overwhelming majority of the group's total mass, both visible and dark. Together, they account for perhaps 90% of all stellar mass within the local group. The remaining members, while numerous, contribute only modest fractions to the total gravitational budget. Andromeda appears in northern hemisphere skies as a faint smudge visible to the naked eye under dark conditions. Ancient astronomers catalogued it as a nebulous object, without understanding its true nature. Only in the 1920s did Edwin Hubble demonstrate that Andromeda lay far beyond the Milky Way, a separate galaxy comparable in scale to our own rather than a gas cloud within our stellar system. The distance to Andromeda measures approximately 2.5 million light-years, making it the most distant object visible to the unaided human eye. The light you see from Andromeda tonight began its journey before the genus Homo evolved on Earth. When those photons departed their source, our ancestors were Australopithecines walking the African savanna, not yet having developed the enlarged brains that would eventually contemplate the cosmos. For most of astronomical history, Andromeda was assumed to be the larger sibling in this galactic pair. Its visible disk appears more extended than the Milky Way's when viewed from outside, and early mass estimates suggested Andromeda contained significantly more stars. Our galaxy seemed like a respectable spiral, living in the shadow of its more impressive neighbour. Modern measurements complicate this picture substantially. Total mass estimates depend critically on dark matter halos, which cannot be directly observed but can be inferred from gravitational effects on visible tracers. When these invisible components are properly accounted for, the two galaxies appear roughly comparable in total mass. Some analyses suggest the Milky Way might actually be slightly heavier, though uncertainties remain large enough that confident ranking eludes current observations. The mass comparison matters because it determines gravitational dynamics within the local group. The more massive galaxy dominates gravitational interactions, capturing satellites more efficiently and determining the ultimate fate of smaller companions. If the Milky Way and Andromeda are truly comparable, neither dominates the group absolutely. Instead, they function as co-equal partners in a gravitational dance that will eventually merge them into a single system. The Triangulum Galaxy, also known as Messier 33, provides the local group's only other significant spiral system. Located approximately 3 million light-years from Earth and roughly 750,000 light-years from Andromeda, Triangulum contains perhaps 40 billion stars spread across a disk, roughly 60,000 light-years in diameter. While substantial by absolute standards, Triangulum appears modest compared to the two dominant spirals. Whether Triangulum is gravitationally bound to Andromeda specifically, or to the local group more generally, remains debated. Its orbital relationship with Andromeda depends on both galaxies' total masses and their relative velocities, quantities known imprecisely. Some models suggest Triangulum orbits Andromeda as a satellite. Others indicate it follows an independent trajectory through the local group. The upcoming collision between the Milky Way and Andromeda will likely sweep Triangulum into the merged system regardless of its current orbital status. Beyond these three spirals, the local group population consists entirely of smaller systems. Dwarf irregular galaxies, dwarf elliptical galaxies, and dwarf spheroidal galaxies orbit around the major spirals or drift through the group on independent trajectories. These smaller members range from substantial irregular systems containing billions of stars down to ultra-faint dwarfs barely distinguishable from globular clusters. The dwarf galaxy population provides important tests of galaxy formation theories. Cosmological models predict that dark matter halos should contain numerous smaller subhalos, each potentially hosting a dwarf galaxy. The number and properties of observed dwarfs constrain these predictions. Current surveys have identified roughly 60 local group members, with ongoing discoveries suggesting the census remains incomplete. particularly for the faintest objects hiding at detection limits. What is certain beyond any doubt is that the Milky Way and Andromeda are falling toward each other. Spectroscopic measurements reveal that Andromeda approaches us at roughly 250,000 miles per hour, a velocity directed almost precisely toward our position. This is not recessional motion caused by cosmic expansion, but genuine approach driven by gravitational attraction between two massive systems. The collision course was first recognized in the early 20th century when Vesto Slipher measured Andromeda's blue shift, indicating approach rather than recession. While most galaxies show redshifts reflecting cosmic expansion carrying them away from us, Andromeda's blue shift reveals gravitational attraction overwhelming expansion. The two galaxies have been falling toward each other since the early universe, their mutual gravity gradually accelerating the approach. Previous estimates place the collision roughly 4.5 billion years in the future. The timing depends sensitively on several factors. The total masses of both galaxies, which determine gravitational acceleration, the tangential velocity component, which affects whether the galaxies will collide directly or initially pass by each other, and the dark matter distribution, which extends gravitational influence beyond visible boundaries. Recent proper motion measurements from the Gaia spacecraft have refined our understanding of Andromeda's trajectory. The galaxy moves not only toward us but also slightly sideways, meaning the collision will not be perfectly head-on. However, the tangential velocity component appears small enough that direct collision remains inevitable. The galaxies will not pass by each other and separate, but will become gravitationally captured in a merger that transforms both systems. More massive galaxies falling toward each other accelerate faster under mutual gravitational attraction. If both the Milky Way and Andromeda are more massive than older estimates suggested, which current measurements indicate, the collision timeline shortens. Recent calculations indicate the merger might commence in closer to 4 billion years rather than 4.5 billion, though uncertainties span hundreds of millions of years in either direction. The collision will not resemble anything in human experience. Stars within galaxies are separated by such enormous distances that direct stellar impacts remain extraordinarily unlikely. The average distance between neighboring stars in the Milky Way's disk measures roughly 4 light-years, over 25 trillion miles. Even when two galaxies containing hundreds of billions of stars each interpenetrate completely, the probability of any two stars actually colliding remains negligible. To appreciate this, imagine two swarms of gnats passing through each other in opposite directions. Each swarm contains billions of individuals, but the gnats are so small compared to the space between them that essentially none will collide. Stars passing through merging galaxies experience a similar geometry, with stellar separations vastly exceeding stellar sizes. The violence of galactic collision occurs through gravitational disruption rather than physical contact. As the galaxies approach, stars begin feeling gravitational pulls from both galactic centers simultaneously. These competing attractions scramble established orbits, flinging stars onto wildly different trajectories than they followed before the encounter. Some stars will be ejected entirely, achieving velocities exceeding the escape speed of the combined system. These hypervelocity stars will fly into intergalactic space, becoming isolated wanderers no longer bound to any galaxy. Computer simulations suggest perhaps 10 to 20% of stars in the outer regions of both galaxies may be flung out during the merger. These ejected stars will drift through intergalactic space indefinitely, their planetary systems, if any, carried along into cosmic isolation. Other stars will plunge toward the combined galactic centers on highly elongated orbits, diving deep into regions they never previously approached before, swinging back out to enormous distances. The orderly circular or mildly elliptical orbits characterizing disk stars will dissolve into chaotic trajectories, sampling the entire merged system. The spiral structures that give both galaxies their visual beauty will not survive this gravitational scrambling. Spiral arms represent density waves, maintaining coherent patterns only because stars orbit in organized fashion. When merger scrambles these orbits, the density waves dissipate. No mechanism will regenerate spiral structure in the disturbed remnant. Gas clouds, unlike stars, will collide directly during the merger. The interstellar medium in both galaxies consists of diffuse hydrogen and helium, with trace heavier elements, spread throughout the galactic disks at densities averaging roughly 1 atom per cubic centimeter. When two such media interpenetrate at relative velocities of hundreds of kilometers per second, the gas shock heats to millions of degrees. This violent compression triggers massive bursts of star formation across the merging system. Gas that might have formed stars gradually over billions of years instead collapses rapidly under shock compression, igniting perhaps billions of new stellar furnaces within a few 100 million years. The merger will briefly transform both relatively sedate spirals into a furiously star-forming system visible across cosmological distances. Such starburst episodes are observed in merging galaxies throughout the universe. The Antennae galaxies, a pair of spirals currently colliding roughly 45 million light-years from Earth, display spectacular star formation triggered by their ongoing interaction. Infrared observations reveal hundreds of massive star clusters forming within the collision zone, each containing thousands of hot young stars that will eventually seed surrounding space with heavy elements through supernova explosions. After several billion years of gravitational wrestling, the merged Milky Way Andromeda remnant will settle into a massive elliptical galaxy. All spiral structure will have been erased. Instead, a bloated spheroid of stars will orbit chaotically around whatever remains of the two original supermassive black holes. Those black holes face their own eventual merger. As the galaxies combine, their central black holes will sink toward the common center of mass through a process called dynamical friction. Stars passing near the black holes transfer orbital energy, gradually draining the black hole's kinetic energy and causing them to spiral inward. The final stages of black hole merger produce some of the most energetic events in the universe. As the two black holes orbit ever closer, they emit gravitational waves carrying away orbital energy at accelerating rates. The final coalescence releases energy equivalent to several percent of the combined black hole mass, radiated entirely as gravitational waves detectable across billions of light-years. The merged black hole resulting from the Milky Way Andromeda collision will contain roughly 100 million solar masses or more, depending on how much gas falls inward during the merger to feed additional growth. This monster will anchor the center of the new elliptical galaxy, occasionally flaring when passing stars or gas clouds venture close enough to be consumed. Astronomers have already nicknamed this future galaxy Milkdromeda or Milkomeda. Our descendants, if any survive that far into the future, will inhabit a completely transformed cosmic home. The familiar constellations will have been scrambled beyond recognition. The Milky Way band crossing the night sky will have been replaced by a diffuse glow from the elliptical spheroid surrounding their position. Whether Earth witnesses, this transformation depends on the Sun's fate. Our star will exhaust its core hydrogen fuel in approximately 5 billion years, subsequently expanding into a red giant that may engulf Mercury and Venus, while severely affecting conditions on Earth. The Sun will eventually shed its outer layers and collapse into a white dwarf, roughly Earth-sized but containing half the Sun's original mass. The timing overlaps disturbingly with the Andromeda collision. The merger will likely commence while the Sun still shines, though it may be entering its red giant phase or have already collapsed to a white dwarf by the time the interaction reaches its most dramatic stages. Any life remaining in the solar system will witness skies utterly transformed by the ongoing galactic merger. The revised understanding of galactic mass and extent affects collision dynamics significantly. The dark matter halos of both galaxies extend hundreds of thousands of light-years from their respective centers, far beyond the visible stellar disks. These extended halos will interact gravitationally long before the visible galaxies appear to touch. This raises an intriguing possibility. The collision may have already begun in regions we cannot directly observe. Dark matter from each galaxy exerts gravitational influence across the void separating them. Where these influences overlap, dark matter particles experience pulls from both systems. The halos may already interpenetrate in the space between visible disks, meaning the merger commenced long ago even as luminous portions remain separated by over 2 million light-years. Computer simulations support this interpretation. When researchers model the approach of two massive spiral galaxies with realistic dark matter halos, gravitational interaction begins when the halos first touch. Tidal forces start deforming both systems before visible disks approach, creating asymmetries in stellar distributions and triggering material flows that precede the spectacular visible merger by hundreds of millions of years. We may be living through the early stages of galactic collision without realizing it, because the initial interactions occur in components we cannot see. The outer dark matter halo of the Milky Way may already feel significant gravitational influence from Andromeda, subtly affecting satellite galaxy orbits and stellar stream dynamics in ways current observations cannot definitively attribute to the approaching collision. Understanding the Milky Way's true scale illuminates how our galaxy reached its current configuration. Spiral galaxies do not emerge fully formed from primordial gas clouds in the early universe. They assemble gradually through cosmic time, accreting smaller systems, merging with comparable partners, and slowly building the structures we observe today. This hierarchical assembly process began shortly after the Big Bang, when dark matter started clumping from initially nearly uniform distributions. Small dark matter halos formed first, merging into progressively larger structures over billions of years. Ordinary matter fell into these dark matter gravitational wells, cooling and condensing to form the first stars, which collected into the first galaxies. The Milky Way has consumed numerous smaller galaxies throughout its history. Each captured system added stars to the growing halo, while contributing dark matter to the invisible envelope surrounding visible populations. The current structure represents accumulated cosmic cannibalism, spanning most of the universe's 13.8 billion year existence. Evidence of these ancient meals persists in stellar populations throughout the galactic halo. Stars born in different galaxies carry distinctive chemical fingerprints, reflecting conditions in their birthplaces. Heavy element abundances, ratios between different elements, and detailed patterns in elemental composition all vary depending on where and when stars formed. These chemical signatures survive unchanged for billions of years, allowing astronomers to identify stellar origins long after parent systems have been destroyed. Kinematic signatures provide complementary evidence. Stars retain memory of their orbital characteristics, even after their parent galaxies have been disrupted and absorbed. Groups of stars sharing unusual orbits, moving in ways inconsistent with formation within the Milky Way disk, likely originated in external systems that merged with our galaxy in the past. The most significant identified merger occurred roughly 10 billion years ago, when a galaxy containing perhaps 1/4 the Milky Way's mass at that time collided with our ancestral system. This galaxy, reconstructed from the debris it left behind, has been named Gaia Enceladus, after the spacecraft whose data revealed its existence and the giant of Greek mythology. The collision was violent by galactic standards. Gaia Enceladus approached on a trajectory carrying it deep into the proto-Milky Way, where tidal forces shredded it over several 100 million years. Billions of stars were stripped from the incoming galaxy and scattered throughout the growing Milky Way halo. These immigrant stars remain identifiable today through their distinctive chemical compositions and orbital characteristics. Gaia Enceladus stars move on radially elongated orbits, quite unlike the nearly circular paths followed by disk populations. They plunge from the outer halo deep toward the galactic center before swinging back out, sampling enormous ranges of galactocentric distance during each orbit. Their chemical abundances show systematically lower heavy element content than stars born in the Milky Way, reflecting formation in a smaller, less chemically evolved system. These forensic signatures allowed astronomers to reconstruct the merger event from the debris remaining billions of years later. Computer simulations reproduce observed stellar distributions when a galaxy of appropriate mass collides with the proto-Milky Way on the trajectory indicated by kinematic data. The match between simulations and observations confirms that this ancient collision actually occurred. The Gaia-Enceladus merger dramatically affected the Milky Way's structure. Simulations suggest the collision heated the existing stellar disk, puffing it up substantially and possibly creating or enhancing the thick disk component observed today. The Milky Way contains two overlapping disk populations: a thin disk of younger stars on nearly circular orbits, and a thick disk of older stars on slightly more inclined and eccentric orbits. The thick disk may represent the original Milky Way disk, heated and thickened by the Gaia-Enceladus impact. Star formation bursts accompanied the merger, as gas clouds in both systems compressed under tidal forces and shock interactions. Heavy element production accelerated during this active period, enriching the interstellar medium that would eventually form subsequent stellar generations. The Milky Way before this collision looked substantially different from the galaxy we currently inhabit. Additional mergers have left their marks throughout subsequent cosmic time. The Kraken event, potentially occurring even earlier than Gaia-Enceladus, may have contributed comparable or greater stellar mass. Evidence for Kraken comes from stellar populations with chemical and kinematic properties inconsistent with Gaia-Enceladus debris, suggesting an independent origin in a separate accreted galaxy. The reconstruction of this even more ancient merger remains tentative, but multiple independent accretion events clearly shaped the Milky Way's early history. The Sequoia merger added material on orbital paths distinct from both Gaia-Enceladus and Kraken debris, indicating yet another independent accretion event. The Helmi streams preserved debris from a galaxy disrupted perhaps 5 to 8 billion years ago. Ongoing disruption of the Sagittarius dwarf continues adding stars to the halo in the present epoch. Each accretion event increased the galaxy's mass while extending its gravitational reach. More massive galaxies possess stronger gravitational influence that attracts additional material for future growth. Success breeds success in galactic assembly, with larger systems capturing more satellites and stripping more material from passing victims. The Milky Way's current heavyweight status reflects a history of successful competition within its cosmic environment. This assembly history means the galaxy's current size reflects past growth rather than primordial conditions. The dark matter halo condensed from density fluctuations in the early universe, but its mass increased through subsequent mergers with smaller halos. Ordinary matter accumulated similarly, with gas and stars from accreted systems adding to the growing galactic inventory. Beyond the local group, our galaxy belongs to still larger gravitational structures representing higher levels in the cosmic hierarchy. The Virgo supercluster encompasses the local group along with roughly 100 other galaxy groups and clusters, spreading across more than 100 million light-years of cosmic space. The Virgo cluster itself, the dominant concentration within this supercluster, contains over 1,000 galaxies centered roughly 54 million light-years from Earth. This massive cluster's gravitational pull affects galaxy motions throughout the surrounding region, including the local group. Our entire galactic neighborhood falls toward Virgo at roughly 300 kilometers per second, a motion superimposed on the larger cosmic expansion. Even the Virgo supercluster forms just one component of a vaster structure, identified in 2014 through careful analysis of galaxy motions across enormous volumes. The Laniakea supercluster, named using the Hawaiian term for immense heaven, contains approximately 100,000 galaxies flowing together within a gravitational basin spanning 500 million light-years. Mapping Laniakea required measuring peculiar velocities for thousands of galaxies, determining how their motions deviate from pure cosmic expansion due to gravitational influences from surrounding matter. Galaxies throughout this enormous volume share a common flow pattern, streaming toward a gravitational concentration that defines the supercluster's center. This mass overdensity, called the Great Attractor, has puzzled astronomers since its discovery in the 1980s. Located roughly 250 million light-years from Earth in a direction partially obscured by the Milky Way's disk, the Great Attractor contains thousands of galaxies whose combined gravity pulls the entire Laniakea supercluster toward a common destination. The Milky Way participates in this cosmic current, carried along with trillions of other stars toward gravitational destiny beyond our immediate comprehension. Our motion toward the Great Attractor measures roughly 600 kilometers per second, relative to the cosmic microwave background radiation, the remnant glow from the early universe that provides a universal reference frame. Yet even Laniakea does not represent the largest coherent structures in the cosmos. Superclusters themselves cluster into even larger filamentary structures, surrounding enormous voids, creating a cosmic web of matter stretching across the observable universe. The Milky Way occupies one small node in this web, connected through gravitational flows to structures spanning billions of light-years. The revised scale of our galaxy reshapes how we understand cosmic significance. The Milky Way was never the modest neighborhood implied by older measurements. Accounting for dark matter halos, extended stellar populations, and circumgalactic gas reveals a galactic heavyweight whose gravitational influence extends across millions of light-years. This scale has profound implications for questions about life elsewhere in the cosmos. A larger galaxy, containing more stars, provides more opportunities for planets to form and for life to emerge. Current estimates suggest the Milky Way harbors between 100 billion and 400 billion stars. The Kepler Space Telescope and subsequent exoplanet surveys demonstrate that planetary systems are the norm rather than the exception, with most stars hosting at least one planet. Conservative estimates suggest billions of potentially habitable planets exist within our galaxy, worlds with conditions potentially suitable for liquid water and the complex chemistry underlying life as we understand it. The actual number could be substantially higher depending on how broadly habitability is defined and how common Earth-like conditions prove across the galactic stellar population. The increased distance scales affect challenges facing any interstellar communication. Signals traveling at light speed require tens of thousands of years to cross even the visible stellar disk. Communication across the full galactic extent, including the extended halo, would require hundreds of thousands of years per message. Any civilizations existing on opposite sides of the galaxy could never exchange meaningful dialogue within biological timescales. Yet the galaxy's gravitational coherence concentrates any potential civilizations within a bounded region that maintains structural integrity across billions of years. The Milky Way has existed in recognizable form for over 10 billion years and will persist for billions more before the Andromeda collision transforms it. Within this vast time span, civilizations may rise and fall. Stellar systems may evolve through their life cycles, but the galaxy endures as a gravitational entity encompassing whatever complexity the cosmos produces. Every atom in your body more complex than hydrogen was manufactured inside stars that exploded before our solar system formed. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all were forged in stellar furnaces scattered across the galaxy and distributed through supernova explosions that seeded surrounding space with heavy elements. You are literally composed of galactic material, organized temporarily into patterns capable of contemplating their own origins. The Milky Way, visible on dark nights, represents just the luminous fraction of a far vaster structure. Beyond that pale band stretch invisible realms dominated by dark matter and hot plasma, reaching toward the gravitational spheres of neighboring galaxies, flowing through cosmic currents toward attractors we can barely detect. We spent centuries measuring only what we could see, assuming visible components represented the complete picture. Modern astronomy exposes this assumption as hopelessly inadequate. The galaxy we thought we knew was merely the bright center of an enormous dark sphere, the illuminated tip of a gravitational mountain extending far beyond the luminous boundary. The traditional measurement was not wrong about the visible stellar disk. The spiral arms, the central bulge, the thin layer of gas and young stars spanning roughly 100,000 light-years across all remain accurately described by those historic observations, but the measurement was catastrophically incomplete about everything beyond that luminous core. When you count the dark matter halo extending hundreds of thousands of light-years in every direction, the sparse stellar halo containing ancient stars and debris from consumed galaxies, the hot circumgalactic medium pervading the enormous volume between disk and virial radius, and the gravitationally bound satellite galaxies orbiting within the Milky Way's sphere of influence, the true scale approaches 2 million light-years. The galaxy is not a disk of stars floating in cosmic emptiness. It is a sphere of gravity, mass, and accumulated history, assembling through cosmic time, extending toward the boundaries of neighboring systems, embedded within structures spanning hundreds of millions of light-years. When you gaze at that pale river of light crossing the night sky, remember what remains invisible. You observe only the fraction that shines, while invisible realms spread undetected in every direction. Dark matter halos interpenetrating with neighboring galaxies, hot gas cycling between disk and halo, ancient stellar streams wrapping the entire system in ribbons of disrupted companions. And you exist within this immensity, composed of its substance, bound by its gravity, a temporary arrangement of galactic matter that somehow achieved the remarkable ability to measure its own cosmic home and contemplate scales that humble every intuition about size, distance, and significance in the universe. We are only beginning to understand.